800,000 people in the United States have a stroke every year. A majority of these cases are amongst adults aged 55 and older. However, that isn't to say that strokes don't occur amongst children and young adults. Out of the three strokes, ischemic, hemorrhagic, and transient ischemic attack, ischemic strokes are the most common, comprising of 80% of all strokes. However, all three strokes can cause symptoms such as difficulty walking, balance disorders, problems with coordination, paralysis in weakened muscles known as hemiparesis, and slurred speech due to facial droop. Therefore, I have developed the following need statement. There exists a need for a way to assist stroke patients with leg weakness in lifting and moving their affected leg in a manner similar to their unaffected leg in order to regain a symmetrical gait pattern for a distance of 100 meters in a public area. Some of the most common tools used in gait rehabilitation are canes, walkers, or even robotic assistants. To get a first-hand account, I shadowed the brain injury clinic at the UVA Battle Building. There I met a patient who had an ischemic stroke and was on the road to recovery. I asked if there were any changes that could be made to current devices, and she told me that she wished that they were more discreet so people wouldn't notice in public, lightweight so carrying it around doesn't become cumbersome, and adaptable so that they can fit in the patient's own needs. The first step in my design process began with research into unconventional areas of gait rehabilitation, which brought me to this video of George, a stroke patient who even after 3 weeks of physical therapy could only get to this point with walking with a cane. However, after the physicians began rhythmic auditory stimulation, you immediately begin to see that George is able to walk in tempo and shows improvements with his walking. Afterwards, they were able to speed George up, and he did so well that they decided to take away his cane. Even after one session, you can see George has made drastic improvements in his walking beats per minute and his walking distance. I then found a report that investigated whether the use of a metronome during walking could reduce excessive variability in gait parameters after a stroke. The standard deviations of the joint angles were calculated and used to give a measure of joint kinematic variability. The variability in the sagittal hip, knee, and ankle angles were reduced to normal values when walking to the metronome. In summation, the metronome cueing resulted in a decrease in variability for step, stance, and joint kinematics. Unfortunately, you can't walk out in public with a metronome in your ear without being a danger to yourself and to others, which is why I decided I wanted to design a device that worked as a metronome but with haptic feedback. My first design was a leg brace that had vibration motors along the length of it. However, it failed to meet any of the design constraints. I then played around with the idea of a sleeve with motors on the thigh, knee, and calf, but sleeves tend to slide off and the design itself did not seem adaptable. My next designs were centered around putting motors in bracelets because those could be put anywhere around the arm or leg and would look relatively discreet. My initial CAD design for a bracelet was very plain and simple. It was just a cylindrical bracelet that would wrap around your arm. Though it seems rigid and stiff in this image, I changed the material to nylon and intended for the straps to be Velcro, though the program is not able to show that. As you can see here, as I zoom in, there's a hole cut out for the motor and a dial to the right of it to adjust the tempo as needed. But before I continued, I wanted to see if I could somewhat verify the results of the previous study that I mentioned. A few friends and I visited Emily in the gait lab and compared our gaits with and without the metronome. Here you see my friend Mary with multiple sensors attached to her body in order for the IR cameras to capture her joint angles. From this angle you can see the two on her iliac crest, and from this angle you can see the 3 sensors along her leg create a polygon, which is what the computers interpret as her leg. This clip shows how the computer sees and processes our gait using input from the IR cameras. Here, my friend Stefan walks to the beat of a metronome. Unfortunately, I was not able to process the data, though I imagine the difference in joint angles was not too significant since we were all people with normal gaits. The next part of my design process was to create the electrical component of the product. I used an Arduino Uno to first create a metronome with a piezo buzzer and potentiometer, and from there I went through multiple iterations of the circuit and the code in order to adjust it for a 5-volt DC vibration motor to get what you see in this clip. As you can see, it starts buzzing at a steady interval. Rotating it clockwise slows down the beats per minute, and rotating it counterclockwise increases the beats per minute. Next step would have been to copy the circuit onto a printable circuit board so that it could function independently as a lone device. Ultimately, my final design was a hybrid between a watch and a bracelet. Here you can see the face would include an AMOLED display that would show you the beats per minute and probably have a dial in order to change how fast you wanted the pace to be. Here you would actually include the printable circuit board and all the wiring electronics that would go below the AMOLED display. And then ultimately, around the back you would put the power supply of the watch / bracelet. And between the bottom portion of the watch and the battery portion would be a Velcro adjustable strap, so you could put it around your leg or your arm, depending.